Hello, everybody, or the four people watching this video. My name is Charlie Romine, and this is my lab on constant motion, or consistent motion. Um, Sort of an introduction. The goal of this lab is to illustrate Newton's first law by observing an object traveling at a constant speed, with no outside forces, because Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an outside force. Discuss deviations in data, so sort of where my computing model and where my actual data sort of veer apart from one another, and then kind of to see what happens with conservation of momentum and things that occur when the net force equals 0. Physics ideas, the momentum, or Newton's first law, which I just sort of touched on, depicted by the graph. It's just a one-to-one slope graph, because constant velocity means a linear position versus time graph, like the one you see on your screen. The momentum principle and Newton's second law and how they're related. So F net equals mass times acceleration, and in this case, F net is theoretically 0. More on that a little later. For the actual experiment, I recorded this cart that is circled in red, which is the system, as it moved constantly along the track. It went about a meter in the video, and then the surroundings are pretty much everything else in that little image there. The push it gets at the beginning, as well as the track and the force that the track has on the cart. Next is the coding. From the base code, there were really only two important things. The first one is the first circle in red, is the velocity vector, which is how the computer model graphed my velocity, and to find that, we simply just took the end velocity and the end from the end position in tracker and added to the initial, divided by 2, found the average velocity. That is what that 0.3245 number is. The next important thing is the time. Each frame in tracker was a 30th of a second, 30 frames per second on an iPhone camera. That's also how the numbers broke down. So we inputted that in the second little red circle there. So the computer model was more accurate. These are the models. Again, that one-to-one slope in the position versus time graph as it moves roughly a meter per second, or a third of a meter per second. And then the velocity versus time graph that shows that it's constant velocity at that 0.325 meters per second. For our results, these are my two graphs. The blue line is the exposition of mass A in reference to time, and the yellow line is the model. As you can see, there's a difference, and I'll get into that in a moment. But the model was not only faster, but also obviously straighter and more consistent because it was computer generated. The actual cart traveled at a slower pace and was not perfectly linear and sort of curves off a little bit, if you can tell. Sources of error, there are two. The first one is friction. As much as we would like to say this lab is about constant velocity and there's no outside forces, the force of friction exists and is prevalent, even with that cart in the track. So that's sort of a first cause for deviation, and why the model and the other line don't line up. And then secondly, the tracking was done by hand. So while tracker does a good job of stopping at each frame and at like equal increments, being ever so slightly off in your click, especially when done on a trackpad, can be sort of difficult and can skew things just a little bit as well. And again, force those two lines a little further apart. Lastly, the what if. What would happen if my axes were changed? I chose the positive x. I think most people probably did. If it were negative, the graphs would both be straight lines in the downward negative direction. And as for what this means, I don't know if you can totally predict how many forces are on an object, but for this scenario, there were 3.